Now that we've covered the power of double machine learning, it's time to talk about something just as important: how we implement these models effectively in real-world scenarios. Machine learning isn't just about choosing the right algorithm, it's also about tuning the model to get the best possible results. That's where hyperparameter optimization, pooling strategies, and computational efficiency come into play. When we extract internal representations from large language models like Llama 3, we're dealing with an enormous amount of data. Each text is transformed into a high-dimensional vector space, often with thousands of dimensions. For example, Llama 3 generates hidden representations where the number of dimensions is equal to the number of tokens in the text multiplied by 4096. That's a massive amount of information. But here's the problem. If we try to work with all of these dimensions, our models become computationally expensive and prone to overfitting. We need a way to compress the information without losing its meaning. Pooling is a technique that helps us summarize high-dimensional representations into more manageable forms. Different deep learning models use different strategies. For example, BERT uses a special classification token called CLS, which serves as a compact representation of the entire input text. Llama 3, on the other hand, uses the hidden states of the last token in the sequence to summarize the meaning of the text. Choosing the right pooling strategy is crucial because it affects how well our model understands the data. If we pick the wrong method, we might lose important contextual information, leading to inaccurate causal estimates. Once we've chosen a pooling strategy, the next step is fine-tuning the hyperparameters of our model. These are settings that control how the model learns, including layer size and depth, determines how complex the model is, learning rate, controls how fast or slow the model updates itself during training, batch size, affects how many samples are processed at a time, maximum epochs, the number of times the model cycles through the entire dataset. Tuning these parameters manually can be time-consuming, but luckily we have tools to automate the process. OPTUNA, for example, is a hyperparameter optimization framework that intelligently searches for the best settings based on performance metrics. Instead of guessing which parameters work best, OPTUNA systematically tests different combinations and finds the optimal configuration. Even with the best hyperparameter tuning, our models need to be computationally efficient. Training deep learning models can take hours or even days if not optimized correctly. That's why researchers rely on techniques like parallel computing, splitting computations across multiple processors, GPU acceleration, using specialized hardware to speed up matrix calculations, mini-batch training, processing smaller chunks of data at a time instead of the full data set. By integrating these strategies, we ensure that our causal models are not only accurate but also scalable, making them practical for large-scale applications in medicine, education, marketing, and policy research. But